Welcome back. This is Dr. Chiranjeevi Manike, Professor and Head of Data Science and Cybersecurity Department, MLR Institute of Technology, Hyderabad. As part of data mining video lecture series, and in this lecture, we are going to discuss one topic in data pre-processing. We have already discussed the different pre-processing techniques, that is, the types of pre-processing techniques. Among those, data reduction is one pre-processing technique. In this, we are going to discuss about the wavelet transforms and also the principal component analysis. So the presentation outline is like we are going to cover the wavelet transforms and also the principal component analysis. Under this wavelet transform, we are going to discuss about a discrete wavelet transform and a discrete Fourier transforms. And then we'll also discuss the general procedure for applying the discrete wavelet transforms. In this principal component analysis, we are going to discuss about what are the principal components and what do you mean by the principal component analysis and basic procedure of principal component analysis, and then we'll see the benefits of principal component analysis. So let us start with the discrete wavelet transforms. And this discrete wavelet transform is one of a linear signal processing technique. When applied to the data vector x, it transforms to the numerically different vector x dash of the wavelet coefficients. So x is a numerical vector with actual data, where x dash is another vector of the same length with wavelet coefficients. So these two vectors are of the same length. So when applying this technique to data reduction, so we consider the tuple as a n-dimensional data vector. That is, for example, if you take a data set, and this is a data set, let us say there are attributes like x1, x2, x3 and so on, xn attributes in this data set. And these are the records, the samples or instances, let us say sample 1, sample 2, sample 3, etc. So each sample will be having values under this attributes x1, x2 and so on, xn. And this we are going to take as input vector to this discrete wavelet transform. So that is this x equal to x1, x2 and so on, xn, depicting the n measurements made on the tuple from n database attributes. These are the n database attributes, and the tuple s1. But here the question is, because the wavelet transformed data are of the same length as the original data, wavelet transformed data are of the same length as the original data. So how can this technique, like discrete wavelet transform, be useful for data reduction? Here the discrete wavelet transform the data that can be, whatever the data that can be transformed with a discrete wavelet transform, that can be truncated. Next, a compressed approximation of the data can be retained by storing only a small fraction of the strongest of the wavelet coefficients. For example, we can define a threshold so that we'll retain all the wavelet coefficients whose values are greater than the threshold, and the remaining we can set to 0. So this technique also works to remove the noise without smoothing out the main features of the data. So it can also be used as a data cleaning technique. So from a given set of coefficients, an approximation of the original data can be constructed by applying the inverse of the discrete wavelet transform. So we apply this discrete wavelet transform to transform the data set into the data set, and then we'll get it back by applying the inverse of the applied discrete wavelet transform. The discrete wavelet transform is mainly closely related to the discrete Fourier transform. It is again a signal processing technique. It mainly involves the sines and cosines. In general, the discrete wavelet transform achieves a better lossy compression. So that is, if the same number of coefficients is retained for a discrete wavelet transform, and a DFT, the discrete Fourier transform of a given data vector, then the discrete wavelet transform version will provide a more accurate approximation of the original data. Hence, for an equivalent approximation, the discrete wavelet transform requires less space than the discrete Fourier transform. Unlike the discrete Fourier transforms, wavelets are quite localized in the space, which contributing to the conservation of local details. So there is only one discrete Fourier transform, but there are several families of discrete wavelet transforms. So there are mainly the few discrete wavelet transforms are popular, which includes the R2, WHs 4 and 6. So from this in this figure you can see the examples of wavelet families. Here you can see the number next to the wavelet name, that is the number of vanishing moments of the wavelets. So that is a set of mathematical relationships that the coefficient must satisfy, and it is related to the number of coefficients. And if you look at the general procedure for applying a discrete wavelet transform, it uses a hierarchical, the pyramid algorithm, that halves the data at each iteration so that the fast computational speed would be achieved. In this procedure, the first step is the length L of the input data vector. That is, we have to check that must be an integer, that is power of 2. This condition can be met by padding the, if it is not, then we can apply the padding, that is padding to the vector with the zeros as necessary, as many zeros as necessary. And second step, each transforms involves applying the two functions. The first applies some data smoothing, such as the sum or the weighted average, and the second performs the weighted differences, which acts to bring out the detailed features of the data. The third step, the two functions are applied to pairs of data points in X, that is to all pairs of the measurements x to I plus 1. So this results in the two sets of the length, where the length of each set would be L by 2. So in general, these represent a smooth or a low frequency versions of the input data and the high frequency content of it respectively. So the two functions are recursively applied to the data sets obtained in the previous loop until the resulting data set obtained are of a length 2. The last step, the selected values from the data sets are obtained in the previous iterations. Those are designated the wavelet coefficients of the transformed data. And if you look at the applications and the various uses of wavelet transforms, the wavelet transforms can be applied to the multidimensional data such as data cubes. And these wavelet transforms give the good results on the sparse or the skewed data and on the data on ordered attributes. And the lossy compression by the wavelet is reportedly better than the JPEG compression, that is the current commercial standard. There are some real world applications of these wavelet transforms, like compression of fingerprint images, computer vision, analysis of time series data, and data cleaning. So now let us look at what do you mean by this principal component analysis. What are the principal components? what do you mean by this principal component analysis, and we'll see the procedure and also the benefits of principal component analysis. So first let us try to understand what are the principal components. So principal components, as we discussed very beginning of this lecture, the high dimensional data, the dimensions of the data, nothing but the features. So here the principal components are the new variables that are constructed as a linear combination or a mixture of initial variables. Like for example, let us say one data set has attributes, let us say A1, A2, A3, A4, etc. This principal component analysis, these principal components, principal components are nothing but a new variables, so which are constructed as linear combination or mixture of these initial variables. So these combinations are done in such a way that the new variables, like new variable is nothing but a principal component. The set of variables are principal components. These combinations are done in such a way that the new variables are uncorrelated and most of the information within the initial variables is squeezed or compressed into the first components. And these principal, what do you mean by the principal component analysis? So principal component analysis, PCA, this is also called as KL method. It mainly searches for k number of n-dimensional orthogonal vectors that can best be used to represent the data, where k should be less than or equal to n. N is the number of variables and where k is the number of principal components. So from this left side of this image, we can see here this here by we can imagine the different components. Like suppose this is the line which is rotating here, that could be one principal component. And next there is a small line, this one, this is another principal component. So in this case, in this principal component analysis, what we are going to do here, the original data are thus projected onto a much smaller space, so that resulting in a dimensionality reduction. Means we are reducing or we are combining the multiple features, or we are removing some features. But what about, because if you reduce the data or if you reduce the number of features, so whether the reduced number of features will give the same information or not, that is the question we will get in this principal component analysis. So first let us try to understand from these figures what are these principal components, so that we'll understand much better of this component analysis. So from the right side of this image, so this one you can see, and this is one principal component, this is another principal component, and there are some dots here, and these are the data points plotted on this two-dimensional space, x and y. And if you could observe this, these data points are spread along this line. This is also called as a vector, and this is the variance, how long, the distance the data is spread out along this line, along this vector. So that is called as a variance. So the more the variance, more information. Okay, so we have to identify such a principal components where the variance is high, so that those components will give a more information. So how long these data points are spread along this principal component? So the distance, this variance, based on this we will select the principal component. So next principle, like suppose from this left side, in my left side you can understand this data, the red dots on this line, and like suppose here you can see how these data points are spreading. In this you can see, and this here you can see, and also like this. So suppose if I join this is the distance, that means the variance at this point, and like suppose this is another variance, and like this is another variance, like this. So the first component, principal component, would be with the higher variance, and then the next principal component will be having a less variance than the principal component 1. So unlike attribute subset selection that will be discussed in the next lecture, this principal component analysis reduces the attribute set, that is by this principal component analysis combines the essence of attributes by creating an alternative smaller set of variables. But whereas a attribute subset selection, which reduces the attribute set by retaining a subset of initial set of attributes. But whereas in principal component analysis, it combines the essence of attributes by creating an alternative smaller set of variables. So that means from this, let us say, like if you go back to the previous slide, and this variance, the more the variance, that means the detailed explained variance, the more the information. So this set of the set of attributes which comprises this principal component analysis, or a new or mixed, or it could be anything, and those attributes will give a much information. So like that, suppose if your data set has 10 features, then we would create 10 principal components. So, and this principal component analysis, we will assign the rank to each principal component. So the first component will be given the highest rank, and then next principal component will be given the next rank, like that. So the initial data can then be projected onto this smaller set. The PCA, this principal component analysis, even reveals the relationship that were not previously suspected, and thereby allows the interpretations that would not ordinarily result. If you check the basic procedure, how the principal component analysis would be applied, but here we are not going to discuss any numerical example. We are going to look the steps in this principal component analysis. The first step is the input data, those are normalized so that each attribute falls within the same range. As we discussed in the previous lecture, suppose one data, let us take one data set, in that the salary data range would be like suppose one, let us say some 10,000 to 1,50,000. That is the salary range. Let us say this salary range in a department. And the other remaining all other features, that the range is small. And if you plot this data on a two-dimensional space, then obviously this salary field, this attribute dominates the rest of all the attributes. So for that purpose, we have to normalize the data so that we can clearly see the relationship between all the attributes. That means this first step helps to ensure that the attributes with the large domains will not dominate attributes with the smaller domains. And PCA computes the k orthonormal vectors that provide a basis for the normalized input data. These vectors are unit vectors that each point in a direction perpendicular to the others. Like for example, let us say, and this is a two-dimensional space, and this is a principal component 1, PC1, and the next principal component should be orthogonal to this principal component 1. This is PC2. Okay, because the principal component 1 will give as much information as possible, whereas the principal component 2 will give the next information, that is whichever is left by the principal component 1, that will be explained by the principal component 2. So that's why we have to, and these principal components should be in orthogonal, that means perpendicular to each other. Next, principal components are sorted in order of decreasing significance or strength, like the variance, based on the variance. The more variance, more information. So the first principal component will be with the high variance, and then little small than the first one, like the decreasing significance or the decreasing strength. We have to make such arrangement. So the principal components essentially serves as a new set of accesses for the data, that is providing important information about variance. That is, the sorted accesses are such that the first axis shows the most variance among the data, the second axis shows the next highest variance, and so on. Next, fourth step, because the components are sorted in a decreasing order of the significance, the data size can be reduced by eliminating the weaker components, because as we discussed many times in the previous lecture, as in this data pre-processing, whatever the features a data set has, all the features may not be having the equal importance. So that we could eliminate the features by, we already discussed like a correlation analysis. So by using this principal component analysis, because we sorted these principal components as per the decreasing order of the significance, so the least significant principal components will be eliminated. So using the strongest principal components, it should be possible to reconstruct a good approximation of the original data, because that principal component will explain more about the data set. So then let us look at what are the benefits of principal component analysis. The principal components can be applied, analysis can be applied to ordered and unordered attributes, and it can handle the sparse data and the skewed data. Multi-dimensional data of more than 2 dimensions can be handled by reducing the problem to the 2 dimensions. The principal components may be used as inputs to multiple regression and also the cluster analysis. But in comparison with the wavelet transforms, the principal component analysis tends to be better at handling the sparse data. So that means the principal component analysis would be recommended if your data set is more sparse, whereas the wavelet transforms are more suitable for data of a high dimensionality. So let us summarize what we have discussed in this lecture. So in this lecture, we mainly discussed about the two data reduction strategies. One is the wavelet transform, and the second one is the principal component analysis, PCA. The wavelet transform, we discussed what do you mean by wavelet. This is mainly like whatever we discussed in this lecture, like discrete wavelet transform and DFT, discrete Fourier transform. These are mainly used in a signal processing. So these methods are used as a data reduction techniques. And we already discussed a pyramid algorithm, that is to apply this wavelet transform. That is, we discussed the steps. And next, in this principal component analysis, we discussed about what is principal component analysis and what is principal components, how the principal components are ordered as per the variance, and we already discussed about the basic procedure of a principal component analysis, and then benefits of principal component analysis, and we also compared with a wavelet transform, where the wavelet transforms are suitable and where the principal component analysis is suitable, and also other uses. Thank you for watching this video.